December 14th, 1972. Gene Cernan climbed back into the lunar module, the hatch closed, and the moon fell silent. For 53 years, that silence has remained unbroken by human presence. A generation was born, lived, and aged without ever seeing a human being venture beyond low Earth orbit. But today, the waiting ends. Look to Launch Pad 39B at Kennedy Space Center. The silence is about to be shattered. It is January 23rd, 2026, and the countdown has officially begun. The abstractions of sometime soon are gone. NASA has locked the target. Mark your calendars, February 6, 2026. This isn't just another satellite deployment. This isn't a trip to the space station. This is humanity, finally reclaiming its birthright to explore the deep void. But as the clock ticks down to that February 6 window, we need to talk about the machine that will take us there, and the incredible engineering hurdles that almost kept it grounded. Why is the launch happening now? And is the hardware truly ready for the violence of re-entry? Today, we witness the return of the explorers. Before we discuss the schedule, we must respect the beast that makes it possible. Standing vertically on the mobile launcher is the Space Launch System, the SLS Block 1. It is a machine of staggering power. Standing 98 meters tall, it is the most powerful rocket currently operational in the world. When those 4 RS-25 engines and the twin solid rocket boosters ignite, they will unleash 39 million newtons of thrust. To put that in perspective, that is 15% more power than the legendary Saturn V that took Apollo to the moon. It creates enough energy to power a major city, condensed into a controlled explosion that lasts just 8 minutes. Crucially, the majority of this power, about 75%, comes from the 2 white boosters on the side. These are not simple copies of the Space Shuttle boosters. They have been upgraded with a 5th propellant segment. Each second, these giants burn through 6 tons of polybutadiene acrylonitrile, providing the raw muscle needed to punch through the thickest part of the atmosphere. Between them sits the orange core stage, holding over 2 million liters of super-chilled liquid hydrogen and liquid oxygen. At the bottom, the 4 RS-25 engines are veterans, literally. These are modified Space Shuttle main engines, hardware with a flight heritage that has already proven itself on previous missions to low Earth orbit. But this time, they aren't going to orbit. They are pushing the Orion spacecraft to nearly 40,000 kilometers per hour, fast enough to escape Earth's gravity well. The engineering required to keep this stack stable is immense. The sound suppression system alone will dump 1.5 million liters of water on the pad in seconds just to prevent the acoustic energy from tearing the rocket apart. This is the hardware we have been waiting for, and after months of uncertainty, it is finally ready to fly. Just a year ago, seeing this rocket ready for a February 6 launch seemed impossible. We were looking at delays that threatened to push us into late spring or even summer. The engineers faced 2 critical enemies that threatened to ground the fleet. First, there was the life support system. Engineers discovered a design flaw in the motor control circuitry for the valves that regulate airflow and CO2 scrubbing. In a spacecraft, redundancy is life. The team had to physically access the Orion capsule, open the pressure vessel, and replace these critical components with hardened electronics capable of withstanding the voltage spikes that cause the concern. In deep space, you cannot fix a broken valve. It has to be perfect. But the bigger shadow hanging over the program was the heat shield. During the uncrewed Artemis I mission, the ablative material, the AVCOAT, didn't behave exactly as the models predicted. Instead of burning away smoothly, small pieces liberated from the shield, creating char loss. This created a risk that the thermal protection could be compromised during the high-speed return. NASA faced a brutal choice: redesign the entire shield, a process that would delay the launch to 2027, or find a smarter way to fly. They chose the latter. The engineering teams achieved a massive victory in trajectory analysis. They didn't change the shield, they changed the physics of the return. By utilizing a skip entry maneuver, the capsule will dip into the atmosphere, bounce back up like a stone skipping on a lake, and then descend for a final splashdown. This distributes the thermal load over a longer period, reducing the peak heating rate and preventing the specific conditions that cause the material to shear off. This solution was verified by months of wind tunnel testing and supercomputer simulations. It allowed mission managers to pull the schedule back to the left. The wet dress rehearsal is complete. The data is clean. February 6 is the plan. So, when the candle lights next month, what is the plan? Artemis II is a mission profile unique in the history of spaceflight. It's much more aggressive than a simple loop around the moon. Unlike Apollo, they won't shoot for the moon immediately. The crew will spend the first 24 hours in a high Earth orbit, looping around our planet with an apogee of 60,000 kilometers. This is a critical safety box. It allows the crew to test the manual controls, life support, and waste management systems. They will even disassemble and reassemble hardware in orbit to prove they can handle in-flight repairs. Crucially, if anything fails during this phase, the burn to return home is short and safe. Once they give the go, the interim cryogenic propulsion stage, the ICPS, ignites for the translunar injection. They will travel approximately 10,300 kilometers beyond the far side of the moon. This is the hybrid free return trajectory. It's a stroke of orbital genius. It uses the moon's gravity to naturally sling the spacecraft back to Earth. If the main engine fails at the furthest point, physics, not propulsion, will bring them home. However, this trajectory comes with hazards. The crew will pass directly through the Van Allen belts, zones of intense charged particles trapped by Earth's magnetic field. Orion is equipped with radiation sensors and a dedicated storm-sheltered area where the crew can retreat to if solar activity spikes. Furthermore, they will be conducting the optical navigation test. In the event of a total communication loss with mission control in Houston, the crew must prove they can navigate back to Earth using only star trackers and onboard cameras to calculate their position, just like ancient mariners used sextants. This isn't just a joyride. It's a stress test for the deep space navigation, the radiation shielding, and the human endurance required for future landings. The hardware is ready, but the heart of this mission is human. 4 astronauts have been training for 2 years to handle every alarm, every fire, and every anomaly this ship can throw at them. Commanding the mission is Reed Wiseman, a veteran naval aviator and test pilot. His primary responsibility is the safety of the crew and the execution of the mission timeline. He knows how to handle high-performance machines in high-stress environments. In the pilot seat is Victor Glover, an elite engineer and test pilot. Glover's role is critical during the proximity operations demonstration, where he will manually fly the Orion capsule to rendezvous with the spent upper stage, a practice run for future docking with lunar landers. Joining them is mission specialist Christina Cook. She is already a legend in the field, holding the record for the longest single spaceflight by a woman. Her experience in long-duration focus is vital for a deep space mission. She will be managing the internal cargo and leading the science experiments on board. And finally, mission specialist Jeremy Hansen. An experienced fighter pilot from the Canadian Space Agency, Hansen is fully integrated into the NASA workflow. His presence underscores the technical partnership between the two nations. He has played a key role in developing the geology training for future lunar landings, ensuring that even on this flyby, the crew is observing the lunar surface with the eye of a geologist. These 4 individuals are not just passengers. They are test subjects and operators. For 10 days, they will live in a space roughly the volume of 2 minivans, proving that humans can once again live and work in deep space. We must, however, look at the horizon. Artemis II is the bridge, but Artemis III is the destination. The landing mission relies on the SpaceX Starship HLS. While development in Texas has been rapid, the challenges ahead are formidable. The architecture for the landing requires not just one launch, but a campaign of orbital refueling tankers. NASA and SpaceX must master the transfer of cryogenic propellant in zero gravity, a technology that has never been demonstrated at this scale. This puts huge pressure on Artemis II. NASA needs a perfect flight this February. A flawless mission proves that the SLS and Orion architecture is bulletproof. It demonstrates that the transportation leg of the journey is solved. This buys the program the political and technical capital it needs to bridge the gap until the commercial landers catch up to the schedule. The waiting is over. The rocket is vertical. The systems are powered. For 53 years, we have looked at the moon and remembered what we used to do. Next month, on February 6, we look at the moon and see what we are about to do. The Artemis generation is finally taking flight.